Okay, Assalamualaikum and good day. So today we're going to cover on introduction to register. Basically, we're going to cover on the first part here, which is we try to understand what is clock gating, and then also how this load control feedback being done in a register. The rest of the topic we're going to cover in our next lecture. So basically, first we have to understand what is a register. So if you guys remember in digital electronic 1, you guys already went through regarding the flip-flops and also latches. Right, so basically what is register? Register is just a group of flip-flops that being used to store the data. So why register? Because the advantage that they have on the speed, as we know that within a computer itself there are many type of memories, such as the hard disk, the main memory, and also the cache, and also the closest one to the processor, which is the closest one to the ALU, is the register. So register is one of the important component in a modern processor. So that's why we're going to cover on what is register, so that we understand how does a register function. Alright, so what good are registers? So basically register, normally flip-flop can only store one bit. If you remember in digit 1, so we look at the flip-flop. So flip-flop can also can just cover one bit. That's why we are having the register, so that we can have a multiple bit. Because if you look into the computer application, normally this software, they are using the integers or single precision floating point numbers that are 32 bits long. So just imagine the data that being processed normally in the size of 32 bits long. So that's why you need to have a place where you can store a huge number of bits, such as maybe 8 bits, 16 bits, or it can go up until 32, 64, or 128 bits. So that's where the register comes into the play, right? So we need to have a place to store a set of bits, 8 bits, 16 bits. So that's the function of having a register. So how we do it? So we just use a multiple flip-flop. So for example, if you want to store 4 bits, that means we need to have 4 flip-flops. If we need to store 8 bits, that means we need to have 8 flip-flops. If we need to store 16 bits, that means we need to have 16 flip-flops for our registers. So why register being picked to be used? Because this is the fastest memory that you can have compared to main memory, and also it helps the processor to store data temporarily. Just imagine the processor have a lot of data to be processed. After you process the data, sometimes you need to store the data somewhere within the processor itself. So that's why they use register to store the data temporarily, and it can be reused again to process something, or it can be sent to be stored inside the main memory, or can be stored inside the hard disk itself. So like I stated before, so the number of bit is directly proportional to the number of flip-flops. Let's say you have 8 bit of register, that means you have to use 8 number of flip-flops. So this is the function of register. You can use normally for storing data, and then you can also use the register to manipulate information. We're going to look into examples such as shift right or shift left. You can use register to shift the number. So if you look into shifting, then the register, it is the simulation of the arithmetic operation. We're going to go into example after this. Alright, so this is how a basic register looks like. So we can store multiple bits just by putting a bunch of flip-flops. So for this example here, we are using 4D flip-flops, 1, 2, 3 and 4. Right, so this is how the circuit looks like and how the connection looks like. So this is the data. D3 is bit 3, D2 is bit 2, D1 bit 1, D0 bit 0. So let's say for an example, you have 4-bit number 1 0 1 1. So this is your bit 0. So this is bit 0 and this is your bit 4, right? So, or in other words, we call this as, this is LSB, least significant bit, and then here the 1 bit 4 here is the MSB, most significant bit. So this most significant bit 4 will be, it goes into D3 here, and the LSB bit 0 here will go into D0, and the rest just follows, right? And then it also being connected to clear signal. This is just want to clear the flip-flop so that you can have a fresh data, new data inside the flip-flop. And it also need to be connected to clock. So if you guys recap on digit 1, this is the main difference between the sequential circuit and also the combinational circuit. Alright, so flip-flop is the type of sequential circuit where it's depend on clock and also it has feedback, right? Okay, so this is how the basic register looks like. So as we all can see, this is the clock. So as the clock goes high, and then it going to update the data. So this is clock here, right? So every time the clock is high, it's going to go and read the data here. So for example, it is 1011. So when the clock is high here, it's going to update the data here. So Q3 here gonna be 1, and then Q2 gonna be 0, Q1 gonna be 1, Q0 gonna be 1. So based on the data that we feed into, right? So this be the Q3, Q2, Q1 and Q0 now become 1011, and this is how the symbols of the flip-flop looks like, right? So whenever you design a circuit, right, you don't want to bring the whole details of the circuit, because you're gonna, let's say you have like 100 register, right? So you don't want for the circuitry to look too complex. So we have a simple symbol that represent the flip-flop itself. So this is how we represent it. So as you can see, it's just a square box here, and then it's gonna the number of the names of the input gonna be written down here, D0 until D3, and also the output gonna be written down here, Q0 until Q3, and we can also see clock here and also clear signal. Alright. Okay, load enable. So transfer of new info into register is referred to as loading the signal. So whenever you want to bring in new data inside the register, like here, let's say you want to bring new value inside the register, so the process is called as loading. So parallel loading means that when all bits loaded simultaneously on clock path. So here you can see here is being connected to common clock source. So then we feed in the value here 1011. So whenever the clock is high, simultaneously all these 4D flip-flops going to update the value. So the process of updating the value from input to the output of flip-flop is called as loading. So it's a parallel loading. So we do it in parallel. And then we also have a control signal. It's used to control the clock cycle. We're going to look into example of this. And then by using this control, input clock paths are prevented from reaching the register when its content is not to be changed. Okay, we're going to see into example what does it mean by that. Okay, so by adding a parallel load operation, so we have like 4 bits of input here and also 4 bits of output. Alright, so how can we store the current value for more than one cycle? So this is how we do it. So we look into example here. So if the LD is equal to 0, the register going to keep its current content. Okay, how does that happen? Alright, so let's see here. So when it is 0, then it's going to recycle whatever value that they have here. Okay, for example, I mean, this just want to give you guys an example. So we have 1011. So when the load is 0, I mean, it's going to neglect or just ignore, whatever data that you put here. It's going to continuously repeat the same value here, 1011. That is meant by when the load signal is 0. So it's going to keep its current content. It's not going to update it with a new value. But if the LD is equal to 1, the register will store a new value. So here, look at the example here. So let's say you have another signal here. So the next signal that you feed into here, let's say 0, 0, 1, 1. So whenever the LD is equal to 1, you're going to replace the value here. So whenever the clock signal is high, then 0 will be going through the D flip-flop here, and then 0 on the D2, and then 1 here, and also 1 here. Alright? Okay, that is meant by LD1. So the register will store a new value taken from inputs D3 until D0. And this is how the diagram looks like. I mean, try to familiarize yourself with the diagram, because later when we work on the lab, right, so you guys gonna see this kind of symbols, right? So then when you look at the symbols, then you can process it. Okay, they have a 4 inputs, D0, D3, and they have clear, load, and also clock input here, and also they have 4 outputs here. I mean, this must be 4 bits flip-flops. Okay, this is the circuit that they use to control, the input of the loading process into the register. Okay, as we can see here, they are using OR gate here, and then there's an inverter at the load input. So and then here is how the symbol of the flip-flop with clear and also load signal looks like. Alright, so we can see here the signal input of the clock, and then here's the load signal. So whenever the load is we can see whenever the load is 0, so the output from the XOR here gonna be always 1. Why? Because let's turn on my pen here. Whenever the input is 0 here, then because of the inverter it becomes 1, and then we know as XOR gate, right? So XOR gate, when it is 0 0, the output will be 0, 0 1, the output will be 1, 1 0, the output will be 1, 1 1, the output will be 1. So as long as the input to the load is 0, because of the inverter, it's been inverted into 1. That's why we can see the output from the XOR gate here is always 1. Okay, but then oops, okay, this eraser here. Okay, let's erase. Okay, alright. Okay, when the input is equal to 1, so let's say the load is equal to 1, what happened here is being inverted into 0. When here is 0, so whatever that comes from the other input of the XOR gate, which is the clock, will be sent to the output. So that's why when we see here, when the load is 1, we can see the output signal from the OR gate is just following the clock signal. So this is when the data transfer happened at the flip-flop, at the positive edge of the clock. So this is how we can have a circuitry to create a load control signal. So we can control whenever we want to have the input of the flip-flop to be load to. Alright, so so this method is known as clock gating. Alright, so clock gating, this is just the, what you call it, the name, right? So clock gating basically just means you control the clock. Whenever you want to let the clock to go into your flip-flop circuit, or you want to block the clock so that the clock cannot pass through here and nothing will happen. So it just remain as it is before. Alright, so basically that is clock gating. Okay, but there's a problem whenever we apply clock gating in the circuit. So what's the problem? The gated clock to flip-flop clock skew of gated clocks with respect to clock or each other. So what is skew? Skew is clock signals arrive at different flip-flops or register at different times. Okay, this is just want to give you example. What does this mean? You know, the skew means. So we know that whatever clock or signal within this chip, right, or the processor, it is the electrical signal, right? So it is just an electron moving within the circuit. So we know, whenever electron pass through, of course there is a delay, right? Just to give you example here, right? So let's say there's a wire here. So we know that within the wire itself, right? There are a lot of, you know, items or molecules, right, inside there. So whenever the electron try to pass through, right, of course there's a resistance, right? So the time taken from the electron to move from point A to point B will take, maybe like some X nanosecond, right? So as the wire is longer, of course the X will be higher, or the delay will be higher. So whenever the signal, the clock signal pass through a gate, for in this example, it's gonna pass through the OR gate, right? So of course when they pass through OR gate here, the OR gate itself will increase the delay. So whenever the delay is increased, so just imagine, so the clock signal here, it has to travel from this point until to the flip-flop D0 here, right? So of course the time taken for the clock signal to reach point here, let's say this is the FF or flip-flop 3, right? Of course the time taken for the clock signal to arrive at flip-flop 3 will be different with the time taken for the clock signal to arrive at flip-flop 0 here. Why? Because there's a delay along the wire, and of course there's a delay mainly comes from the OR gate. Alright, so okay, what else we have to cover here? Okay, clock gating. Okay, so this is the same example. So whenever the LD is 0, we have discussed before, whenever LD is 0, what happens is that the clock flip-flop becomes 1, and there will be no data transfer occurred. Why? Because the data transfer will be occurred whenever there is a changes from changes of signal from 0 to 1, or there's a transition from 0 to 1. So in this case here, the output of the OR gate here is just flat 1, so there's no changes of state from 0 to 1 or from 1 to 0. So that's why whenever there's a 0, so whatever value that are already inside the flip-flop will remain as it is. For example, if the value is 101001, so it's going to remain. So as long as the LD is 0, the value will remain as 1001. Right? So you can see here the main function of this circuitry here is to control the clock. So it prevents the clock signal from goes in the circuit. So that's why you can see here it just remain as 1. So there's no clock occurs. And then whenever the load signal is 1, so we are allowing the clock signal to goes in, and it will update the value of the flip-flop. So our previous example, the value is 1001. So let's say the new value here is 1111. So whenever the clock signal is high here, at this point it's going to update the new value. Right? So yes, it is. So the changes occur here. Alright, so it's just going to update the different. So 1 will go here, and then 1 will go inside here, and 1 will go inside the flip-flop 1, and then 1 also will go in the flip-flop 0. Right, so I mean whenever the load is 1, it will allow the clock to pass and let the flip-flop update to the new value from the input D0 until D3. Alright, so yeah, I mean the clock gating, but since gates are added to the clock signal, there are timing problem similar to those lectures. So LD must be kept at 1 for the correct length of time and no longer. Alright, and then the clock is delayed a little bit by the OR gate. So in more complex scenarios, different flip-flops in the system could receive the clock signal at slightly different times, like the example I've shown before. So this clock skew can lead to synchronization problem. Alright, so there are two challenges here. The first one is the clock skew, like I've explained before, because of the delay that caused by the gate itself. And then the second one is that the timing. Alright, so let's say for an example here, right? Okay, let's say we have a numbers of data, right? Okay, let's say data 1, right? Data 1. So data 1 is 0 0 0 1, right? And then we have data 2, data 2, which is 0 0. Let's see the bit. Zero 1 0, and we have data 3. We have data 3, which is 0 1 0 0. Right? Okay, let's say at first we have the data 1 at the output here, so which is 0 0 0 1. Right? Okay, so we want, right, we want this data 0 just for, this is just example, okay? We want the data 0 for just one clock cycle here, right? So the next clock cycle, right, for the next clock cycle we want data 2, which is 0 0 1 0 here, right? Okay, so if you want to have data, I mean different data at every clock cycle, right? So we have to make sure, right, the load signal here is correct, right? Okay, I mean there are few scenarios that can occur here. Okay, let's go into scenario number one. Right, so let's say the load signal is high here, and then it is low here, and then okay, yeah, it's low here, and then it's high here. All right, so the data, the first set of data will be ready within this period of clock time. All right, so as we can see, the first data first is successfully transferred in this phase here, the first phase. Right, this is the first phase within the first clock cycle. But in the second clock cycle, we can see, I mean, look at the red line here that I draw. So just imagine this is the load signal, right? Because we change the load signal to 0, and then we bring it up again into 1, but we bring it up late here. So when we bring it up late here, so we miss the transition here. Whenever we miss the transition here, we miss the second data. Alright, so I mean, this is just to give you example, you know, the problem that can occur when we are using this clock gating. Alright, so a better parallel load circuit. So I mean, this is another alternative. I mean, instead of using this clock gating, we can use a better parallel load signal by having such as, you know, a selection here. So in this case, you can see here we have I mean, this is kind of this is mux, right? One of the component that we can use is a mux. What is mux? Mux is a multiplexer. All right, mux. This is just a short form for multiplexer. What is multiplexer? Multiplexer is a component that you can have to select multiple inputs. So example here we have two inputs, 1 and also input 2, right? And here is a select signal, select. So if this S0 is equal to 0, then let's say this is the output, output, right? So out will be I1. Let's say the S0 is equal to 1, then out will be equal to I2, right? So this is just mux. Okay, in this case here, so when LD is 0, so the flip-flop inputs Q3, Q0, so the input here will be Q3, Q2, Q1 and also Q0 if the LD is equal to 0. That means when LD is 0, so it's choosing the bottom input here. So the bottom input going to be fed into this flip-flop. So whenever the LD is equal to 0, the value will be remain here. The flip-flop value will be remain. It's not gonna be changed into new value. But as you can see here, this is the main difference between clock gating. So the clock signal does not need to pass through any gates like in the clock gating. So you have to pass through the XOR gate, right? But here in this new design, we don't have any gate here. So I mean, we have reduced the delay. So we have a better clock input here. But we need to have extra circuitry, which is the mux signal, to select which input that we want to fit into this flip-flop. So whenever the LD signal, the load signal is equal to 1, it's going to choose the first input here, which is the middle signal, the D1. So D1 is the new value that you want to insert into the new into the flip-flop or into the register. Alright, so Basically, this is how the circuit looks like. You can see here 2 to 1 multiplexer. So this is in terms of gate signal. So we can see here, we have two input, right? Input 1 and also input 2, right? And then so here is the flip-flop, right? So you can see if the load signal is equal to, let's say the load signal is equal to 0, you can see here it becomes 1, and here the input is 0. So, and they are using AND gate here. So when AND gate, right? So the AND gate signal is when it's 0 0, the output is 0. When the input is 0 1, the output is 0. When the input is 1 0, the output will be 0. And when the input is 1 1, the output will be 1. Right? So we can see here, as long as there's one input 0, then the output will always be 0. So in this case here, we can see that input 1 will be neglected, right? So it's going to continuously feed the same, the output from the flip-flop, and going to be feed back into the circuit. So it's going to remain the same value. But if we change the value right now, right, we change it to 0, if we change the value into 1, and then here we get 0, and here we get 1. So whatever input that comes into input 1, it goes in the flip-flop, right? And then the previous value will go in, and then there's a 0 here, this point becomes 0. Alright. Okay, and then here we just going to cover a little bit about the shift register. It is using the same flip-flop concept here, but if you can see, the circuitry is a bit different because we want to shift the input, right? So we can see there are 4 flip-flops here. Right, so we input the value Q0, Q1, Q2, Q3, Q4. So in this case, example shown here, Q0 is equal to 0, 1. So Q0 is equal to 0, Q1 is equal to 1, Q2 is equal to 1, and Q3 is equal to 0. Alright, so whenever there's a positive edge of the clock, right, so the input here 0 will go to the next state here, right? And then the 1 will be input to this flip-flop and goes out here, and then the value here gonna move here, right? And then this new value that you feed in will come in and take this position, right? So that's why you can see here, first value is 0 1 1 0. SI here, the new input that you're gonna feed here is 1. So the next state will be, right, so the next state is, now so it becomes 1 0 1 1, right? So it's just shifting 1 bit, in this case, to the right, right? So that is what is known as shift registers. Alright, so what happened is that the value on the most right here will be gone in the next cycle. You can see here 0 now is gone in the next cycle. The new value, which is 1, is waiting at the signal input here. It's being moved into this 4-bit data. Alright. Okay, so the shift direction, alright, so it's really depend on the interpretation of the signal. Right, so basically if you want it to move to the right, right, so we can take it, like the first example being shown here, right? So let's say Q0 until Q3 we present is A, B, C, D. The SI is X, so the next Q0, Q3 will be X, A, B, C, D. So that means it is shifting to the right. But if you want it to shift to the left, so we just change it, right? So the same signal here, but we just take it as DCVA, and then in this case we are moving it to the shifting it to the left. So basically, I mean, the same circuitry, we can use it for both shift left or shift right, but it's really depend on the manipulation of how you want to interpret the data. So if you want to interpret it as shifting to the right, then you present the data like this example here. If you want it to shifting in the opposite direction, you just change the representation of the data. Okay, so here shift registers with parallel load. You don't worry, after this we're going to see, I mean, the example how this being used in the real computer world, alright, so that we can make sense out of it. So here is the example how the shift register will have the parallel load, right? So the same goes like we did before, right? So we use the marks, and also there's a flip-flop here. So whenever the LD is 0, the flip-flop inputs will be SIQ, means that it's going to shift the input. So whenever the LD is equal to 1, so the flip-flop inputs will have the new input here. So you can see here, whenever the LD is equal to the load signal is equal to 1, it's going to pick the input from D0. But whenever the load signal is equal to 0, it's going to take the bottom signal here. Alright, so you can see here, this is just shifting. So the input that going to go into this flip-flop is the SI, the shift input, that new value that we want to bring in, and then here is Q0. So the output from the first flip-flop here going to move here, and then the output from this flip-flop going to move here. Right, so this occur when the LD is equal to 0. But if the LD is equal to 1, we're going to have new value here. Alright, so we're going to enter new value here, and then after that we will do the shifting process. Alright, so okay, here is the application, right? So when we gonna use this shift register, alright, so normally the computer, right, we have also a serial data transfer. So for an example, like USB, firewire, or a lot of the communication from the computer to the outside world, they are using the serial data transfer. So whenever, but within the computer itself, they are using parallel data transfer. So that's why they need to have a conversion between serial to parallel, and also from parallel to serial. Alright, we're going to look into example. So yeah, we can see here computers typically works with multiple bit quantities. So example, ASCII is 8 bits long, integers up until 32 bits long, right? But sometimes necessary to send or receive data serially. So this is whenever they are communicating with the outside world. Alright, okay. Alright, okay, so receiving serial data, that means we have a serial input, then we want to transfer it into the computer, right, which is processed in parallel type of data. But the serial input device, they are sending the data by using serial data. Alright, okay, so the serial device is connected to register SI. Alright, so this is the input that will be connected. The shift register output Q0 is connected to the computer. Right, so this all four is connected to the computer. Right, so the serial device transmit 1 bit of data per clock cycle. Okay, let's say this is the data 0 1 0 1. Alright, so every clock cycle here, okay, that's good, so it should be. So every clock cycle there is one data being sent, right? So after 4 clock cycles, 1 2 3 4, the shift register will hold for 4 bit. Alright, so I mean here is the first clock cycle 0, right? It's gonna go into here 0. Okay, let's erase it first. Okay, no pen. Right, so 0 will go here first, 0, right, at the first clock cycle, and then second clock cycle the 0 gonna go into the next position. Alright, so let's erase it and then write it again. So 0 will move into Q1, and then 1 here, because this is the second clock cycle, 1 will go here. Alright, now we have 2 value inside the shift register, but we haven't sent the data yet, right? Because we know that the computer want we to send the data in a form of 4-bit size, right? So we haven't reached the 4-bit size yet. Means we just have 2 bits of data, so we have to complete all those 4 cycles. Alright, so we complete all those 4 clock cycles. Now we have the data, all of the data inside the shift register 0, 1, 0, 1. When we have 4 complete data, then this data going to be sent to the computer. Then the new data will comes in, right? So there is a new data that comes in, right? So whatever data, so let's see here the data is 1, 1, 0, 0, right? So after they send this set of data, then they're going to process another set. Okay, sending data serially. Okay, so this is vice versa. So as the computer want to send data to this serial device, right? So they have to change the data from parallel into serial. Alright, so same here. So I mean the computer will send 4 data at one time. So let's say 0, 0, 1, 1 here. Okay, and then 1 bit on Q3 on each clock cycle. Alright, so the data will goes inside here. Alright, so I mean because we see 2 options, right, before this in the shift register. So the second option, when LD is equal to 1, you can have all the input parallelly insert into the flip-flop, right? So our example is 0, 0, 1, 1, right? So 0, 0, 1, 0, 0, 1, 1 will be inserted inside the flip-flop. Okay, so let's say we have clock cycle here. Right. So all this data will be transferred parallelly 0, 0, 1, 1. Okay, what happened is that before the computer is sending new data, I mean this shift register need to send the data serially to the printer here. I mean this is just example, right? So at the first clock cycle, 0 gonna be output here. So we're gonna send 0 here. Alright, so then the data gonna move up. So 0, 1, 1. So and the second clock cycle, 0 will go here, and then we erase it, then just left 1, 1 here. So until 4 clock cycles, we're gonna complete it, right? 1, 1. Right, so when we complete it, then the new set of data comes in. You see the new set of data is 0, 1, 1, 0, right? So it's gonna repeat the same process again. So this is the application when we need to use this shift register. Alright, so the summary of the lecture today. So register is special state machine. I mean, of course, it can store multiple bits of data. So there are several variations from this register structure. We can have parallel loading in and loading out into the register, and we can also have a shifting, of the register, which we already discussed, and also we can use it as a counter and consider a type of register too. Right, so we're going to look into the example later, maybe in the next or coming lecture. So one application of C register is converting between serial and parallel data. This we already discussed the example, right? When the computer want to communicate with the outside world, such as mouse or printer, so they have to change the data from parallel to serial. Same goes when the mouse want to talk to the computer, the data need to be changed from serial to parallel. So most programs need more storage space than registers provide. So of course we need to have RAM to support, because register is pretty expensive to be implemented throughout the processor. So that's why we need to support it by having a RAM to address this problem. And registers are central part of modern processors. It is a must. It's a features that you need to have inside a processor. Right, so I think that's all for our first lecture. So we're gonna discuss more further in our next coming lecture. Alright, thank you so much. See you next time. Bye bye.